Let's talk about a few more non-parametric tests and summarize the advantages and disadvantages of these tests. These guys, Kruskal and Wallace, came up with a non-parametric analog to ANOVA. If you remember, ANOVA can compare the mean between more than two groups. And we've seen that the non-parametric test can be used when the assumptions of such tests aren't met. If we don't have normality or we have an extreme violation of the homoscedasticity, we might be able to use a Kruskal-Wallace non-parametric test, which is just like a generalization of a t-test, and it allows us to compare those medians or those ranks between multiple groups. These are data from 2010 about parental opinions on school closures during a pandemic, the H1N1 flu, and then relating those parental opinions to how often they let their kids play with other kids. Schools were closed to prevent the spread of this disease, and kids ostensibly are supposed to stay home and not play with other kids, but some parents allowed their kids to go out. And here we see some summary data of how often the kids did out-of-home activities, and the parents are split into two groups. Sorry, into three groups. That's what I said, no, but into three groups. Parents who thought the school closure was not appropriate, parents who were unsure, and parents who thought the closure was appropriate. Now, these researchers, I hope, they've looked at their data and decided it's not normal. The mean doesn't make sense, so we can try to do a non-parametric test. They're trying to compare these three groups, so it has to be something that looks like ANOVA. And they get this nice p-value, and you can go anywhere in the world and say, I ran a Kruskal-Wallace test. You can even go to Australia. I ran a Kruskal-Wallace test, and there is a significant difference in the number of out-of-home activities between these three groups. There are even non-parametric analogs for the sort of the more advanced test. If you remember, we did the correlation coefficient for the linear association between two continuous variables, and we called that Pearson's R. And Pearson's R is, well, how much does each point differ from the mean of X and the mean of Y? This is what we call the covariance. And in the calculation of the correlation coefficient, we divided by the standard deviation of X and the standard deviation of Y in order to sort of standardize it on something that went from -1 to 1. But if you notice, the means there's a lot of means in that formula. And if you have data for which the mean is not an appropriate summary statistic, why in the world would you do some other statistic that includes a lot of those means? You shouldn't. That Pearson's R is very sensitive to outlying values because the mean is not very robust. The mean will change a lot when you have large values in your data set. So this guy Spearman, which is great because it's all Pearson's letters just mixed back around. Spearman said, oh, I have an idea. Let me take the data and rank it. And if I rank people's values, then what I'll do is do the correlation coefficient using the ranks. So you basically take that formula we just saw, and instead of plugging in the actual values and the means, you use the ranks of each variable. I'll show you an example of the Spearman's correlation. We'll try to answer the age-old question, more money, more problems. Can money buy you happiness? These are data, real data, in which people were asked about how happy they are on a scale of 1 to 3. And then they were queried about their income. And the income variable was coded in such ways that you might have a category that's like 50,000 to 60,000. And then you check the little box if you're in that category. Now, that's not a number. All right, we can't calculate the mean of that box. But we can still order people on how much money they make. If you're in this box, you make more than the people who are in the box below you. And we can display that data. These researchers took the midpoints of each range. And so this range might be somewhere like here. Now, if we plot out the data, what do you see? It's kind of hard to see any pattern. Can we run a correlation coefficient? No, because the mean doesn't really make sense here. What does mean this? Or what does mean this? Well, we can run this Spearman correlation coefficient. Again, it's one of these non-parametric tests and data. And we get this value. And it says there's a negative correlation between money and happiness, which is a little counterintuitive. It's not that strong, negative 0.15, but it is statistically significant. P less than 0.0001. The negative correlation between income and happiness. But double check, always double check. This is negative. It means as your income increases, your Y variable decreases. And if you look at the Y variable, you'll notice that it's inverse of what you would think. So it's actually the more money you have, the more likely you are to be down on this, the more happier you are, right? The more happier you are. So to summarize about non-parametric tests, they don't have restrictive assumptions. We're saying like, okay, the normality assumption, that sort of stuff, we can let that go. Again, you can bring these tests anywhere in the world and they'll work and people will believe you. And we get rid of some of the sensitivity of the outliers. It allows us to analyze these ordinal data. It's data that otherwise we weren't able to analyze, but by purposefully throwing away the information and taking the data from continuous down to ordinal, now we can analyze it. And the disadvantages of these tests are basically the flip side of those. We have these less specific null hypotheses because we got rid of the idea of any assumptions. Because we got rid of the data, we can't really calculate what is the magnitude. What is the actual difference? I don't know, it's just different. We can't calculate a CI if we don't have any difference. And I think the most interesting thing is this, you lose information. I don't think that's really an advantage or a disadvantage. It's just what this test is. You take your data and you bring it down the data hierarchy so you can analyze it and compare it. And remember, you can't go back up. You can say there's a difference. And in order to see that difference, I changed the data and looked at medians. You can't go back up and make up numbers. So that's a brief introduction to the idea of non-parametric tests. Remember, for most parametric tests, there is a non-parametric analog, and you can just go in and Google it. And usually they deal with the ranks or the medians of the data. You lose some of the ability to talk about specific differences, but you gain the ability to analyze data sets that otherwise you wouldn't be able to analyze. You're basically adding another set of tools into your statistical tool belt.